So what we are going to be talking about for the first half of class, potentially more, is a review of sinusoidal signals and their properties. We're going to spend some time reviewing this concept because we are about to get into what's called sinusoidal steady state circuit analysis. And in sinusoidal steady state circuit analysis, all of our circuits will be excited by sinusoidal signals. Okay. So this is where we get into the portion of the class that has to do with the power that is applied by these wall outlets and all that kind of good stuff. Because while we might call that 120 volts, what that really is a shorthand representation for 171.6 cosine 120 pi t plus whatever phase angle that happens to be at a particular time. So we're going to talk about what all that gobbledygook I just said was by defining what sinusoids are, and then move towards understanding how alternating current power is distributed and used. Well, you're going to be bored for the next half hour then. So characteristics of sinusoids. So let's say that I have a generic sinusoidal waveform. And I will try to draw this as least crappily as possible, but please bear with me. All right, so this guy is a poorly drawn sinusoidal signal, V of t. Our x-axis here is the amplitude of the voltage, V, as a function of time. And this axis here is time itself. Okay. So this sinusoidal waveform is characterized by three different quantities. The first of which is the amplitude, which I'm going to call V subscript M. So it's the magnitude of the voltage, okay? So this amplitude is the maximum value of V of t. So if I say that I have a 3-volt sine wave, that means that it oscillates between positive 3 volts and negative 3 volts at a particular frequency, okay? So that 3 there would be the amplitude of our sine wave. Now, this sinusoidal signal, which I just realized I didn't draw quite right because it has different magnitudes, which obviously doesn't work. So let me fix that. My apologies. Can't do it well. Something like this. All right, so at least now it's roughly all the same amplitude. It's not going further below the x-axis at some parts than it is at the others. I can understand why you would be wildly confused by that because that's not how sinusoids work at all. So sorry for drawing it poorly. All right. So this particular sinusoid and all sinusoids in general are periodic functions, which means that in a certain amount of time, t, they go through exactly one cycle, right? So T, in this case, is the period of the waveform V of T. So way back in engineering 121, you guys learned a relationship between the period of a and its frequency. To recap, that relationship is pretty straightforward. The period is exactly equal to the reciprocal of the frequency, where F here is the linear frequency measured in hertz. Hertz is an interesting unit because it means 1 cycle per second. So if something oscillating at a frequency of 1 hertz completes 1 cycle exactly in exactly 1 second. Okay. What we are going to be dealing with in this class is what's going to be called the angular frequency. Okay. So if 1 cycle of a sinusoid represents that sinusoidal signal processing all angles between 0 and 2 pi. So omega is the angular frequency measured in radians per second, and omega is simply 2 pi times the linear frequency. So we have a direct conversion from angular frequency to linear frequency, just multiplying or dividing by 2 pi as is necessary. Okay. And the last thing we have is what's called a phase angle, right? So phi is the phase angle of the waveform. So before we talk about what that is, I'm going to better mathematically define what our voltage waveform is here, okay? So we'll have some magnitude Vm cosine omega t, which represents how quickly that signal oscillates as time progresses, plus some phase angle phi, okay? So phi represents how far to the left or right we have shifted this waveform in time. What I mean by that is that cosine of 0 should be where our waveform reaches its peak value. But we can see very easily that our cosine reaches its peak value at some t that is not equal to 0. So that means this particular waveform has experienced a phase shift, and that phase shift is quantified by the phase angle. Okay. So changing the phase angle along the axis, excuse me, let me think about this. Changing the phase angle shifts the waveform along the time axis without changing the amplitude or the frequency, okay? So it's literally just shifting that waveform left and right, depending on what the value is, but its amplitude and frequency are fixed. We're just sliding it back and forth along that horizontal time axis, okay? Positive phase angles where phi is greater than 0 cause shifts to the left by delta t is equal to phi over omega. Now this might seem weird to some of you guys, okay? So positive phase angle means we shift our sinusoid to the left. What that is implying is that when we represent time on an axis, where let's consider t is equal to 0 to be the present, everything to the left is what occurred in the past, and everything to the right is what will occur in the future. So a positive phase angle means that we're just making things happen earlier, which is why we shift to the left. And a negative phase angle means we're introducing a delay or causing things to happen later, which is why we shift to the right. It seems counterintuitive, but I am giving you the correct methodology here, okay? So negative phase angles. Where phi is less than 0. Cause shifts to the right by delta t is equal to phi over omega. Okay. So as part of our process as electrical engineers, we will sometimes have to make comparisons between sinusoidal signals. Okay. There are a few very specific rules about doing that correctly. All right. Rule number 1. Says that all functions must be expressed exclusively as sine or cosine waveforms. All right. So let me explain what I mean by that by scrolling up here and taking a peek at this guy again, right? So I called this guy a cosine wave arbitrarily. I could express it as a sine wave by recognizing that a sine wave and a cosine wave are the same thing. They're just shifted by 90 degrees, okay? So I can take any cosine wave and convert it into a sine by adding 90 degrees to it. And I can take any sine wave and turn it into a cosine by subtracting 90 degrees from its phase angle, right? So I can say, I'm going to introduce some trig identities that we're going to have to memorize here. Cosine omega t is equal to sine omega t plus 90 degrees. And the inverse relationship then is sine omega t is equal to cosine omega t minus 90 degrees. So if I want to convert, let's do an example here in blue. If I have VA of t is equal to 7 cosine 33t plus 30 degrees. That is the same as sine 33t plus 120 degrees. All I have to do to convert from one to the other to convert from sine, or excuse me, from cosine to sine is just add 90 degrees to my phase angle. If I didn't have a phase angle, that means the phase angle was 0. So I just add 90 degrees by itself. If I wanted to go in the opposite direction, we can obviously see that we just subtract 90 degrees from the phase angle of the sine function to return back to the cosine, right? In electrical engineering, we use the cosine function as the basis of all of our sinusoidal waves. Okay? Everything is going to be related back to a cosine function. So if we ever have a sine, we are going to wind up using these simple trig identities to express it as a cosine to be able to do our math, and I'll explain why that's so important later on in this class. Okay. Our second rule for comparing sinusoidal signals is that all functions must be expressed with a positive amplitude. So negative cosine omega t is the same as positive cosine omega t plus or minus 180 degrees. It literally does not matter if you add 180 degrees or you subtract 180 degrees. It gets you to the same point on the unit circle. Okay. So I hear a lot of people ask, well, when should I add it and when should I subtract it? It does not matter. They're identical. Okay. Similarly, negative sine omega t, excuse me, is equal to sine omega t plus or minus 180 degrees. Let's call this rule 1, 2, excuse me, identity 1, 2, 3, and 4. Only 5 more to go. All right. Our third rule is that all functions must have the same frequency. Okay. There aren't any trig identities to get around this guy. We can't convert a function of one frequency to a different frequency. Its frequency is fixed, right? So if we're trying to analyze signals and we're dealing with 2 different frequencies, what we'll wind up having to do is employing the techniques of superposition so that we can only look at one frequency at a time. Okay, we'll get into that in a couple of days. All right. So one of the most confusing comparisons that we will have to do is determining whether a particular waveform is leading or lagging another waveform. Okay. So if I have a sinusoidal signal try very hard to make my amplitudes the same here. So let's call this guy in green VA as a function of time. And let's call this guy in red here VB as a function of time. Like so. We might be asked to tell which of these signals is leading or lagging in comparison to the other, okay? You can absolutely do this by looking at a time domain representation of these signals, okay? So let's talk about what leading and lagging means. If a signal leads another signal, that means it reaches its peak amplitude at an earlier point in time. So, which one of these signals is leading, green or red? So green reaches its peak earlier than red, if we are comparing the two peaks that are closest together, which we don't necessarily have to do. So it's kind of a trick question, all right? So green reaches its peak earlier. So green is leading red. And alternatively, we could say that red is lagging green, okay? So if a signal lags another signal, that means that it reaches peak amplitude at a later point in time. Okay? So establishing whether or not a signal is leading or lagging another signal using a time domain representation is fairly straightforward. Determining how much that waveform leads or lags its cohort is an entirely different bag of cats. In the time domain, I think it's very difficult. So what I would like to introduce you guys to is a concept called a phase diagram that will allow you to easily determine whether signals are leading or lagging, okay? So what a phase diagram is a snapshot of a sinusoid at a very specific instant in time. It can be any instant in time, but t is equal to 0 is usually the easiest, okay? So let's say that I have some signal. Actually, let me change the colors here so this will be easier. Let's say that I have VA of t is equal to 6 cosine 15t plus 12 degrees, and VB of t is equal to 8 cosine 15t minus 30 degrees. What I can do is effectively make a polar plot, right? So here corresponds to 0 degrees, up here would be 90 degrees, here would be plus or minus 180 degrees, down here would be 90 degrees. So I could represent VA by a vector that has a magnitude of 6 and is oriented 12 degrees above our horizontal axis. So this is a phase representation of VA of t, where this angle right here is 12 degrees. Similarly, I could say that VB of t would be this guy. Where this angle is exactly 30 degrees away from the horizontal axis, but it shifted down because our angle is negative. So if we wanted to figure out how much VA leads VB, what we would need to do, I'm going to erase this 30 degrees here because it's going to get in the way. Is start our measurement from here and go counterclockwise, okay? So measuring counterclockwise from our reference tells us how much A leads B. The reason why counterclockwise is leading is because A is then in turn more positive, so it's occurring at an earlier point in time, right? If we went in the clockwise direction, we would determine by how much A lags B, because we're making the angle get more and more negative. So we're delaying the signal by more and more, okay? So based on this diagram, so counterclockwise is leading. Clockwise is lagging. By what angle does VA lag VB? Anybody have any thoughts on how we might figure that out? Chester. So clockwise, so VA leads VB by 42 degrees. Okay. VA lags. We start measuring from VB. That's our reference, right? So we want to know what VA is doing with respect to VB. So we measure from VB, and we need to go all the way around this angle, right? So that would be this portion right here is 60 degrees. This portion right here is another 90. This portion right here is 90. This portion right here is 90 minus 12, which is 78 degrees. We add all those guys up, and that tells us what angle VA lags VB by. Does that make sense? Okay. So, sure, give me just a second to add these numbers together. 60 plus 180 plus, oh, of course, my calculator's being dumb. That'll work too. Yeah, 360 minus 42 is 318. So if we want to know by what angle VA lags VB, we look at where VB is, and then we start measuring from VB in a clockwise direction. So we start here. Crap, I didn't mean to erase my axes. Let me fix that real quick. So we start at where VB is at, and then we just keep going all the way around until we hit VA. So when we're going in a clockwise direction, we're measuring lagging. We're measuring in a counterclockwise direction, we are measuring leading. Okay. You are going to have some homework problems on web work regarding this concept. you are going to get frustrated. Okay, now let me explain why. The method that I have given you here is perfect and flawless because I am perfect and flawless. We both know that's true. But this method legitimately is perfect, okay? Does everything it needs to do. It's very simple to understand. The problem is web work can't tell the difference between 0 degrees and 360 degrees and 720 degrees, etc. It can't tell the difference when angles are 360 degrees apart. So while doing it this way, we would get 318 degrees. Web work might say, it's actually -42. They're the same angle, but web work doesn't know the difference. So if you do my method and it tells you you're getting the wrong answer, add 360 degrees. If that doesn't work, subtract 360 degrees. One of those will be correct, okay? It's just because web work is dumb, all right? So I'm just trying to save you that headache of doing everything right and then getting super pissed off and it's all web work's fault. Benjamin.
I don't know if you explained it, but is it always going to be that counterclockwise is leading and clockwise is lagging?
Yes,
Okay.
always. Because if we look, so counterclockwise is lagging, excuse me, counterclockwise is leading because we're looking for angles that are more positive, which means that that waveform is hitting its peak value earlier in time, which is the definition of leading, right?
Okay.
So counterclockwise is always leading, clockwise is always lagging. All right. Have I beat you guys? Drew.
So if the question was, what angle does EB lag VA? You would measure from VA going clockwise.
Exactly right. And so we would see that it's 42 degrees. Yep. So we would go 12 degrees down to the horizontal axis and then 30 degrees more. 12 plus 30 is 42, and we're done. Absolutely correct. Any other questions on this? It seems trivial until you do it, and then you're like, oh crap, what is this again? And then web work only makes it worse by not interpreting the answers correctly, okay? This seems straightforward. I'm legitimately happy to explain it again because it's going to save you headaches if it's not clicking, all right? So anybody got any more questions on this, or can we move along? All right. So we are about to analyze a circuit in the time domain, okay? Before we do that, I'm going to introduce more trig identities that are going to pop up. All right. So we already have numbers 1 through 4, but I'll write them down again just for the sake of argument. Identity number 1 was cosine of omega t is equal to sine of omega t plus 90 degrees. Rule number 2, or identity number 2, I'm sorry, is sine of omega t is equal to cosine of omega t minus 90 degrees. Number 3 was negative cosine omega t is equal to positive cosine omega t plus or minus 180 degrees. And identity number 4 was negative sine omega t is equal to positive sine omega t plus or minus 180 degrees. So this is how we manipulate things, change from cosine to sine and vice versa, get rid of negative magnitudes, all that kind of stuff. Easy and straightforward things. Now, we are going to have to add sinusoidal signals together. And that can be a bit of a pain in the butt. So the next several identities are all going to be involved in that process, depending on how our math pans out. So our first one is sine of alpha plus beta, where alpha and beta are both angles, is equal to sine alpha cosine beta plus cosine alpha sine beta. Number 6, cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. I did not get the sign in the middle incorrect. It is supposed to be a minus sign there. Remember this guy. I'm going to put a star by it. It's going to be the one that winds up getting used the most, and it is actually got a very handy shortcut built into it that I'll explain in a little bit. Number 7 is sine alpha minus beta. And that is sine alpha cosine beta minus cosine alpha sine beta. And number 8 is cosine alpha minus beta. And it is cosine alpha cosine beta plus sine alpha sine beta. So those are all wind up being used to add and subtract and manipulate, perform simple mathematical operations on sinusoids. We will wind up doing multiplication of sinusoids at a later date, but I'm not going to bog you down with that rule just yet. Another one that we are going to use today that is probably the most important trig identity in all of electrical engineering is this guy. Cosine omega t plus phi plus j sine omega t plus phi is equal to e to the j omega t plus phi. Okay. Take a minute to look at what this is. A rectangular form complex number is equal to a polar form complex number by exactly the relationships that we discussed the other day, right? This would be an amplitude of 1 and a phase angle of omega t plus phi in this case. So we have 1 cosine angle plus j 1 sine angle. It's exactly the identities that we introduced the other day, okay? So this guy right here is wildly important. It's called Euler's identity. And it seems like it's going to be a huge pain in the butt, but it's actually a magic tool that turns trig into algebra, right? So with these 9 trig identities given, let's analyze the circuit. Okay. Sure. Am I allowed to continue on? Okay. All right. So we're going to analyze this circuit twice, but in very different contexts, okay? And the first is to explain something that we talked about briefly in transient analysis, okay? So let's say, for the sake of argument, that I have a 2 amp source connected to a 4 ohm resistor connected to a 2 Henry inductor. Sorry, thank you. And I want to determine this quantity Vs. What is it? How could I do it and what is it? Let's start there. Okay, so we could apply Kirchhoff's voltage law, and we could say that the voltage drop across the resistor plus the voltage drop across the inductor is equal to that voltage source Vs. So that would be Vs is equal to VR plus VL. Well, VR here is just 2 amps multiplied by 4 ohms. And VL here is just 2 Henrys multiplied by the derivative with respect to time of 2 amps, which will give us exactly 8 volts. Anybody have a problem with my application of Kirchhoff's voltage law here and determining what this voltage is? All right. So one key thing that I want to point out here, and it's going to be very important, is that when we have a circuit operating at DC steady state, our responses will all be DC signals. That's exactly what we have seen. Okay. So if we put a DC signal in that 2 amp source, the voltage drop across our resistor is a DC quantity. The voltage drop across our inductor is a DC quantity, and therefore the voltage drop across our source also has to be a DC quantity. So if I have that circuit, but I apply time varying current, which I will define in just a moment, where this is still a 4 ohm resistor, and this is still a 2 Henry inductor, and I'm trying to find Vs of t if Is of t is 2 cosine 10t amps. Actually, I'm going to write this slightly differently. 2 cosine 10t plus 0 degrees amps. I'm being explicit that there may be a phase angle here. I can expect my voltage waveform to be of the form Vm cosine 10t plus some phase angle theta v degrees volts. So effectively, all I'm arguing here is that if I put a DC signal in, or if I excite my circuit with a DC signal, I get a DC response. By the same vein, if I excite my circuit with a sinusoidal signal, I should expect to get a sinusoidal response, where the amplitude might be different and the phase angle might be different, but the frequency is going to be the same. Is everybody okay with that? Okay. So if we wanted to determine Vs of t for this circuit, we could do the exact same methodology that we applied to our DC circuit, right? So we could say that we have some voltage Vr of t, and we have some voltage VL of t, and we know that Vs of t is equal to Vr of t plus VL of t. Kirchhoff's voltage law doesn't care if we have a DC circuit, an AC circuit, or anything in between. Kirchhoff's voltage law always has to work. Okay. So Vr of t is just going to be 4 ohms times our current Is of t 2 cosine 10t amps. And VL of t is going to be L, which is 2 henries, times the derivative of IS of t, again, 2 cosine 10t amps. So this first term is pretty straightforward. I'm going to have 8 cosine 10t volts. The second term is going to be a little bit more difficult because now I have to do calculus because there's just derivative-based relationship between current and voltage in an inductor, right? So when I take the derivative of this guy, I'm going to have 2 henries times 2 amps times -10 per seconds, giving me an overall total of -40 volts cosine, excuse me, a -40 volts sine 10t. Here's the problem. I get, by applying Kirchhoff's voltage law, an answer that is the sum of sinusoids, not a single sinusoidal function. Okay? So this bit was fairly easy and straightforward. Making this guy look like a single sinusoidal function is where this math gets to be a bit of a pain. All right? So let's walk through it. Trig identity number 6, right? Says that cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta, right? I'm going to make a very small adjustment to this. I'm going to say that A, some arbitrary amplitude multiplied by cosine alpha plus beta is the same as A cosine alpha cosine beta minus A sine alpha sine beta. So I'm just adding in some amplitude term here to kind of help us out because our cosine and sine functions have amplitudes that aren't 1. So if we let alpha be the quantity 10t, right? 10 radians per second multiplied by time is just an angle. Everybody okay with that? Okay. So if alpha is equal to 10t, then that means 8 must be A cosine beta, and 40 must be A sine beta. Is everybody okay with that? If I need to explain what I'm doing here, I'm happy to do it. This is going to get a little wacky. Everybody okay? I'm sorry, what was that, Joy? So if this bit right here represents cosine 10t, since alpha is equal to 10t, then A times cosine beta must be that magnitude 8. Right, so look, effectively, what's that called? The method of undetermined coefficients, where I'm saying the coefficient of the sine portion on the left-hand side equals the coefficient of the sine portion on the right-hand side. The coefficient of the cosine portion on the left-hand side has to equal the coefficient of the cosine portion on the right-hand side of the equation. Okay, so I'm saying that this guy right here is equal to this guy right here so that I can express a cosine beta and a sine beta in terms of known quantities. Does that help explain it at all? Okay. So I have two equations and two unknowns. So I can, Benjamin.
I don't know if I'm thinking of this the wrong way, but when I see it as like a cosine beta and a sine beta, is that kind of like the different components when you have a vector? It's like a final.
It turns out that you're absolutely correct, with one small caveat, which I will talk about in a little bit. Okay. So your mind is heading in the right place here. Okay. So if I take a cosine b and square it, and add to that a sine b and square it, what I get is a squared cosine squared beta, excuse me, not b, plus sine squared beta, which is exactly equal to a squared, right? Using good old trig identity, sine squared plus cosine squared is equal to 1. So I can say that a is one of the two numbers that I'm solving for is simply the square root of a cosine beta squared plus a sine beta squared, which is exactly the same as the square root of 8 squared plus 40 squared, which gives us 40.792 volts as our amplitude of our single sinusoid expression. Everybody okay with that? To determine beta, I can recognize that the tangent of beta is equal to the sine of beta divided by the cosine of beta. And therefore, the tangent of beta is a sine beta over a cosine beta, right? If I put an a quantity in the numerator and the denominator, I'm still okay. And so from this, beta is then the arctangent of a sine beta over a cosine beta, or the arctangent of 40 over 8, which comes out to be 78.690 degrees. So putting these two results in, I find that Vs of t is equal to a 40.792 cosine nt plus 78.690 degrees. So I was able to take that sum of two sinusoidal signals and force it to look like a single sinusoidal signal having a particular amplitude, frequency, and phase angle, which exactly match the response form that I was expecting to get. So let me ask you guys a question. How much of a pain in the ass was that? Pretty tedious, right? This result here and this set of math that we did works for this circuit and this circuit alone, which is awful. Absolutely awful. Okay. So what I would like us to do is to revisit this step right here. Okay. But I'm going to do something slightly different. All right. I can say, excuse me, I'm going to leave this 8 cosine 10t bit alone. So 8 cosine 10t. So I have negative 40 sine 10t, which is going to be the same as positive 40 sine 10t plus 180 degrees. And then to convert that to a cosine signal, I will subtract 90 degrees from it. And so I will have 8 cosine 10t plus 40 cosine 10t plus 90 degrees. Okay. That's just using those first couple of trig identities. Now what I'm going to do is probably going to make next to no sense to you all. And that's perfectly okay for right now. All right. I'm going to convert this to a complex number. Actually, it's going to be the sum of 2 complex numbers, right? I'm going to represent 8 cosine 10t by its magnitude 8 and its phase angle 0. And I'm going to represent 40 cosine 10t plus 90 degrees by its magnitude 40 and its phase angle 90 degrees. And I would like for you guys to use your calculators and give me the result of that operation in polar form. What'd you get? 40.792 with an angle of what? 78.69 degrees. So we get the exact same magnitude and the exact same phase angle in one trivial step. We have completely eliminated all of our calculus, all of those god-awful trig identities by converting our signal into an exponential complex relationship, right? Or polar form complex number. Okay. So that process that we just did is called working the circuit in the frequency domain or in the phasor domain, okay? So before we hammer home what exactly that means, I want to explain why it works, right? So you don't need to write this part down per se, just kind of listen along. This is not something even remotely you might be tested on, all right? So if we have a linear black box network representing any circuit that we're dealing with in this class, and we excite it with an input signal, I'm going to call it a voltage signal just for the sake of argument, x1 of t. We should observe a response, which I will just happen to represent as a current here, doesn't particularly matter, as y1 of t, where if x1 of t is a voltage, let's do it the other way around, actually. Let's do it exactly what we did. X is a current. Y is. So we observed that if we put in an input x1 of t of the form Im cosine omega t plus some phase angle theta I, we got a response of the form Vm cosine omega t theta b, which is exactly what I was talking about 20 minutes ago, right? So if we put in a cosine function, having a particular frequency, amplitude, and phase angle, we get out a cosine function that has a different amplitude, or it may have a different amplitude and may have a different phase angle, but gives us the same frequency, right? What if I repeated this? Same linear black box network. I put in a new current. X2 of t. And observe an output Y2 of t. So in this case, let's say that X2 of t is equal to Im sine omega t plus some phase angle theta I. What should we expect for our response? If we put in a sine function, probably expect to get a sine function out. Anybody have any problem with that? Do any of you remember what the homogeneity or scaling principle of superposition said? Ian.
You have a linear network.
Exactly right. So if we scale our input by some scalar non-time variant quantity, we scale our output by the same quantity. So if I scale my input by a factor of the imaginary operator j, my output should scale by the imaginary operator j as well. So even though that's not a real number, it works because it's time invariant. So if we now apply the additivity property of superposition, meaning I apply both of those input signals at the same time, what should I expect to see at my output, right? So let's take our linear black box network. Let's apply a signal x1 plus x2. According to the additivity property, I should get at my output y1 plus y2, where in this case, our total input signal x is Vm cosine omega t plus theta v plus j Vm cosine, sine omega t plus theta. Oh, dang it, these should be currents. I apologize. I am theta I am here, theta I. Using Euler's identity, that trig identity number 9, this is the exact same thing as I am e to the j omega t plus theta I. And I should get back a total response y of t of the form Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v. I'm going to leave it in that sense, okay? So if I excite my system with an exponential input, my response will be an exponential output. But here's the real interesting thing, okay? The real part of my exponential input, the cosine term, gives me the real part of my exponential output. And the imaginary part of my exponential input contributes all of the imaginary part of my exponential output. So I can, instead of using that sinusoidal function, I can apply an exponential representation and get the exact same result because the real part of the input corresponds to the real part of the output. That's why we can convert this time domain signal into an exponential number and get the exact same result as we did analyzing the circuit entirely in the time domain. So Euler's identity is I hesitate to say magical, but it's a wonderful tool that converts all of this terrible trig to algebra. Okay, so let's rework that problem very specifically using an exponential representation. Okay. So if I have a waveform here, IS of t, here's my 4 ohm resistor, here's my 2 Henry inductor, and I am trying to find this quantity, Vs of t. Let's say that Is of t is the real part of Im e to the j omega t plus theta I. Therefore, we expect Vs of t to be the real part of Vm e to the j omega t plus theta v. And in this case, Im 2 amps, omega is 10 radians per second, and theta I is 0 degrees. Right? We're going to use the same numbers that we had before, and obviously we should get the same result, but we'll see that it takes considerably less math, right? So yes, so Vs of t will still be equal to Vr of t plus VL of t. Okay. Kirchhoff's voltage law is Kirchhoff's voltage law. It must be satisfied. Vr of t is now going to be 2 ohms times 2 e to the j 10t amps. And then we're going to have VL of t as 2 Henrys times the derivative of 2 e to the j nt amps. So when I do the VR part, that's just 2 multiplied by 2 exponential blah, blah, blah. So that's going to look like 4 e to the j 10t volts. What happens when I do the derivative of this guy here? Okay. So when I take the derivative of this exponential, the derivative of the exponential is a bit easier to deal with than the derivative of the sinusoid, right? So in this case, or in every case, when I have a sinusoidal steady state problem, taking the derivative is just multiplying by j omega, right? So when I take the derivative of 2e to the j to the 10t, with respect to time, 2 is a constant, so nothing happens to it. I have e to the j 10 multiplied by t, So I take a J10 out, which is just J omega. If there were a phase angle there, what would happen to it? It'd go away because we'd be taking the derivative of a constant, right? So anytime you take the derivative here, you're just multiplying by J omega. You're transforming trig into algebra, all right? So this is going to look like plus J. And so now we're going to have 10 times 2 times 2, which is 40. Yes. Yes, it is 4 ohms. Thank you. That was a dumb mistake on my part. Yeah. 4 ohms, making this part right here 8. Thank you. So 10 times 2 times 2 is 40. So we're going to have J40 e to the J 10t volts. Now I'm going to have to do something else here. We talked about this briefly in class on Wednesday, because today is Friday, right? If I look on complex plane, and I go 1 unit in the imaginary direction, J in rectangular form is 0 plus J. And in exponential form, that would be 1 e to the J, excuse me, 1 e, yeah, 1 e to the J 90 degrees. Yeah. So if I treat this J as 1 e to the J 90 degrees, that makes this bit right here look like 40 e to the J 10t plus 90 degrees. And then we can easily see that we have 8 angle 0 degrees plus 40 angle 90 degrees, where I'm suppressing that omega dependency. I'm suppressing the frequency term. That is the exact operation that we did to get that shorthand result. Now, this method here that I just did, where I was very meticulous and everything, probably took a little bit longer than it needed to as well. Okay, it's quicker for sure. Doesn't involve a whole hell of a lot of trig identities and weird stuff, but it's still taking too damn long. So what we are going to do is what electrical engineers much smarter than me have discovered in the past. We are going to develop what are called phasor relationships for all of our circuit elements and for all of our voltage and current signals, okay? So what a phasor relationship is it's just a shorthand notation for expressing sinusoidal signals as a complex number. Yes. RE for the real axis. Okay. So let's talk about voltage and current phasors first. All right. So let's say that I have a voltage waveform. V of t is equal to Vm cosine omega t plus theta v. And I have a current waveform, I of t is equal to Im cosine omega t plus theta I. This is a time domain representation of these waveforms. Using Euler's identity, we could say that V of t is just the real part of Vm e to the j omega t plus theta v. And I of t is simply the real part of Im e to the j omega t plus theta I. This is what I called the mixed domain. Complex numbers, but there's still a time dependency. So now we're going to take that next leap into the phasor domain. And this is a very difficult process, okay? So in the frequency domain, or the phasor domain, we will have a voltage phasor V with a bar over it, representing that it's a complex number, and we carry this information. Magnitude of phasor. Full stop. Same with our phasor current. We will have a magnitude and a phasor. The magnitude of our phasor voltage is the magnitude of our time domain sinusoid. The phase angle of our phasor voltage is the phase angle of our time domain sinusoid, and the exact same thing for our current, okay? So to go from the time domain to the frequency domain, we literally keep the amplitude, keep the phase angle, and throw everything else away because it doesn't matter. All right? One very important thing here is that we must express all of our time domain signals as cosine functions. And it's because of Euler's identity. If we don't do that, we're going to run into issues. Okay, so everything in the time domain needs to be converted into a cosine function before we turn it over to the frequency domain. So to hammer this concept home, if I have VA of t is equal to 17 cosine 3 pi t plus 11 degrees, what should the phasor domain representation be? (17 angle 11 degrees). If I have VB of t is equal to 13 sine 71 t plus 96 degrees. What is my phasor representation of VB? Benjamin, what did you say? So it won't be with an angle of 96 because we have to convert that sine function to a cosine function before we go to the frequency domain, right? So how do we convert that sine function to a cosine? Subtract 90 degrees. 13 angle 6. We can do more of these examples all day. They won't get any more difficult. Actually, let's introduce one where things maybe do get a little bit wonky here, okay? And this will help with a couple of your homework problems now that I'm thinking about it. Let's say that we have VC of t is equal to 12 cosine 11 11t plus 9 sine 11t. To convert this, it will be easier to convert each of the individual portions into phasors first and then add those guys together. So what's interesting here, that would look like 12 angle 0 degrees plus 9 angle minus 90 degrees, right? Somebody tell me what that is. It's a polar form complex number. $15 angle negative 36.87 degrees. Could you tell me what that is as a rectangular form complex number? I just want to do this to illustrate something real quick. 12 minus 9j volts. So we can, realistically, you never have to actually do this operation. But for whatever reason, there are multiple annoying as shit homework problems that you have to do this operation, okay? So what I'm trying to point out here is that you can go from that phasor representation, right, where you have a magnitude and a phase angle, to the sum of sinusoid representation, thank you, where the only difference there is the sign on the imaginary part, or the sign on the sine part, okay? And it's because of that trig identity that says cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. So that's where that minus sign comes back around. So you can save yourself a ton of time on all your homeworks and this, that, and the other, and all of this dumb, stupid, crazy trig math that you're being asked to do by using complex numbers correctly. Okay, they're wonderful, wonderful things. All right. Yes.
So doing our conversion to polar using Euler's identity, dropping off the angular frequency. So if you wanted to go backwards, there would be no way to know the frequency.
So that is a fair thing, right? So this frequency domain representation does not carry that frequency term. You have no idea what omega is unless you are told, right? So that is one of the downfalls of frequency domain analysis, right? If I have a signal 3 cosine 4t plus 6 degrees volts and 3 cosine 87.33 t plus 6 degrees volts. They both have the exact same frequency domain representation. We're throwing away that angular frequency part. For any problem that you would have to work, if you ever need to convert it back into the time domain, you do need to know what the angular frequency is. Typically speaking, on a problem like that, though, you start in the time domain, convert everything into the frequency domain, analyze the circuit in the frequency domain, and then use that to get back to the time domain. So if you ever started in the frequency domain, the problem has to stop in the frequency domain unless you're told what omega is. That's a very fair observation. We are suppressing or completely eliminating that information. It does not get brought back in or magicked up. We have to know what omega is. Jesse. Pardon? Okay. So I'm saying that 12 cosine 11t has a magnitude of 12 and a phase angle of 0 degrees. 9 sine 11t is the same as 9 cosine 11t minus 90 degrees. So the 9 is the magnitude and the negative 90 degrees is the phase angle when I represent that sine bit as a cosine function. If I want to convert to the frequency domain, I must convert my sines into cosines, which is exactly what we did here in part B. All sine functions must be expressed as cosine functions. So the 12 minus J9, if you put 15 angle negative 36.87 degrees in your calculator and tell it to convert it to rectangular form, that is exactly 12 minus J9. The final answer would be 15. It depends on if you want your answer to be in polar form or rectangular form. What you're asked for is what it should be in. I was trying to illustrate the point that the rectangular form of the complex number contains the exact same information that the sum of the sinusoids we were trying to avoid had. Right? The reason why we had to do all that terrible math was because we had to force something cosine 10t plus something else sine 10t to make look like a third something cosine 10t plus a phase angle. All right? I'm just trying to illustrate all those different relationships between the time domain functions and the frequency domain functions. Okay. Generally speaking, I prefer my answer for all voltage and current signals to be in the polar form there, carrying only the amplitude and the phase angle, because that most directly matches the information that's carried in a time domain representation, right? Because a complex number in polar form has an amplitude, a frequency, and a phase angle. And a sinusoid in the time domain has an amplitude, a frequency, and a phase angle. Those two things directly correlate. All right, I've talked for 90 minutes straight. So I'm going to stop talking. We're actually ending this lecture a little early. I wanted to talk about what's called impedances next, but we'll kick things off on Monday with that. I do have an in-class assignment here that I legitimately feel that if you've been paying attention, you can do the first 3 problems in about 10 minutes. If you want to take a crack at it, you are welcome to do so. If you want to say, you know what, it's Friday, it's almost Halloween, I want to go put on a costume and I didn't say that. I thought it very much, but I didn't say it. Yes, if you want to do that, have fun.